Hey guys, how you doing? I hope you're doing well. I'm gonna try and make a couple of adjustments. See what I can do. There we go. That's much better. Sorry, it was driving me crazy. It was gonna bug me if I didn't fix it. So let's see if we can get this started. So I've discovered that I had some problems with one of the videos, so I'm re-recording this one. Hopefully you will find this helpful. This is the bonding and dot diagrams video, so I'm going to go ahead and share my screen if I am not. And let's get this one shared and we can take a look at bonding and dot diagrams. So this is our bonding and dot diagrams information. So we will share this. This is a lot of stuff that we're going to be talking about. It's not going to take as long as it looks. We do have a little bit of review material that we're going to talk about first. So let's go ahead and get into that first. So from last time, we have a 64.85 grams of Na3PO4 resolved in 725.3 milliliters of water. What's the molar concentration of that solution? Well, the first thing I need to do is to get to moles per liter, because that's molarity, which is the molar concentration. So we want moles per liter. In order to do that, I need to figure out what the molecular weight, the grams per mole of Na3PO4 is. So the first thing I need is my handouts from D2L. So I'm going to see if I can pull out my handouts from D2L, and where is that? Okay. So D2L, going to one of my shells, content, course documents, exam handouts. Here are my molecular weights, but I'm going to actually go to the table for this. And I'm going to cheat a little bit. So I have a spreadsheet that I've put together of all the molecular weights, not only from the periodic table there, but also from Alex, because it makes my life a little bit easier. So this has all of the Alex molecular weights and the periodic table data. So I did that so that I could work with these numbers when I'm trying to do some of these calculations. I also have this, so I'm going to pull this off on the other side. That way we can work with both of those. So I'm working with 64.85 grams of the Na3PO4. And so I know that I have a molecular weight that I need to calculate for this. And I've actually got this in scientific notation, so I'm just going to put this back into a number format. So I want my molecular weight here, and I'm going to put in 3 times the sodium. So I need to find my sodium, which is here. I'm going to use the periodic table number, which is right there. And then I need to add my phosphorus, which is right here. And I need to add 4 times that oxygen number, which is right here. So that's the molecular weight for that. And again, I'm going to put that back into just the number format. So that gives me 163.94. And again, that's 3 times the sodium plus the phosphorus plus 4 times the oxygen. So that's Na3PO4. So that's the molecular weight of that material. Now, if I take that mass, I divide that by the molecular weight, that tells me the number of moles of that material that I have. I can actually put that over here. And that tells me the number of moles of that material that I have. Now that I have the number of moles, I can divide by the volume in liters. And so that's equal to the volume that I have in milliliters. 725.3 divided by 1,000. And so then if I wanted my molarity, that's going to be equal to the number of moles divided by that volume in liters. And so that gives me this number, which is right here, as long as it's in the number format, and that's 0.55 moles per liter. So that's the answer that I would report there is 0.55 moles per liter. The second question says the solution above is diluted by taking 15.32 milliliters of solution and diluting it to a final volume of 25 milliliters. What's the final molarity of that solution? So again, here, just detailing what I did. I took that 64, come on, 64 0.85 grams divided by the 163.94 grams per mole. I then divided that by that 163 point, no, I divided that by my 725.3 milliliters. And then I converted that 1,000 milliliters per liter. And that gave me 0.55 molar. So it's moles per liter. Okay, so that's the calculation that I did there. The solution above is diluted by taking 15.32 milliliters of solution and diluting it to a final volume of 25 milliliters. It's the final molarity of that solution. Now this is a dilution of solutions. So dilution of solutions is done by M1 B1 equals M2 B2. That's how we handle our dilutions of solutions. I'm looking for the final molarity, so I want M2, which is the secondary molarity. So my M1 is that number that I just solved for, that 0.55 molar. My V1 is the volume of that solution that I'm going to use, which is that 15.32 milliliters. And the V2 is going to be that final volume, which is 25 milliliters. So I can plug all of those lovely numbers in and solve for M2. So M2 is going to be equal to M1 B1 divided by B2. And so I'm going to plug in M1, which is 0.55 molar. I'm going to multiply that by my V1, which is 15.32 milliliters, and then I'm going to divide that by 25 milliliters. And of course, I love to do things in Excel, so I'm going to take my M1, which is 15.32. I'm going to take my V1, which is V2, which is 25 milliliters, and I'm going to say that's equal to the number that I calculated, the 0.55, times my M1 divided by my V1 divided by V2. That gives me 0.33. And so this is equal to 0.33 molar. And that makes sense to me because it should go down. Now I can put that number over here, but it's not going to fit very well, which is why I put it on the other side. Okay. So that makes sense to me. It should go down, and it should go down roughly be 2/3 of what it was in previous to that. Okay, so I'm cool with that. Now, a 64.38 milliliter sample of an unknown acid HX is reacted with NaOH. One HX reacts with one NaOH to give NaX and water. So I have an equation that I can write for. I'm going to pull this down here, and I'm going to go plus NaOH reacts to give me NaX plus H2O. That's the equation, and because that's what they told me. It says a 64.38 milliliter sample of an unknown acid. So I have 64.38 milliliters of that unknown acid reacts with 27.32 milliliters, 27.32 milliliters of NaOH. That's 0.0200 molar. What's the molarity of the acid? So I wrote down all the information that I had about the HX and the NaOH in my reactants, and it wants to know what's the molarity of that HX. So I know that's what I need to solve for. Now I always start with what I know the most about. So I'm going to start with my information about the NaOH. And I always start with that volume. So 27.32 milliliters. Now, since I know that this is in moles per liter, I'm going to convert that from milliliters to liters. So there's 1,000 milliliters in 1 liter. That cancels the milliliters. And then I'm going to multiply that by the molarity, the 0.0200 moles of NaOH in 1 liter of NaOH. Now cancel the liters. I now have moles of NaOH that I'm working with. I know there's 1 mole of NaOH in my balanced equation that reacts with 1 mole of HX. That's for my balanced equation right here. So now I have moles of HX. Now in order to get to molarity, I need to divide by the volume. And I need that to be in liters, but I know what the milliliters are. So I'm going to divide by the milliliters. 64.38 milliliters. And then I'll convert that 1,000, not 10,000, 1,000. 1,000 milliliters for 1 liter. So that cancels the milliliters and will leave me in liters, and that'll give me moles per liter of that HX. I like to do things in Excel, so I equal 27.32 divided by 1,000 times 0.020 divided by 64.38 times 1,000. I know I'm multiplying and dividing by 1,000, so I really don't have to do that, but my head explodes if I don't. So there we go. And when I do that, I end up with 0.0085. So I check my math, 27.32 divided by 1,000 times 0.02 divided by 64.38 times 1,000. And looking at those numbers, I see that I have a very small amount of NaOH and a very large amount of HX. So that makes sense to me, okay? So that makes a lot of sense as far as the number that I'm looking at, 0.0085 molar, okay? So I know that that NaOH is more concentrated than my HX due to the change in volume, the difference in the volumes that I'm looking at. That NaOH has to be a lot more concentrated because I use a much smaller volume than my HX. Okay, so that's what I've got there. Cool with that. Now, if the mass of the acid added to make the solution was 686.71 milligrams in 1 liter, what is the molar mass of the acid? Okay, that's the first thing. So I know that this was 0.0085 moles per liter, right? So I know how many moles this was. And I know it's a 1 liter solution, right? So if I know it's a 1 liter solution, then I know how many moles it is. I can take that 0.0085 moles per liter times the 1 liter, and that tells me that it's a 0.0085 moles moles of HX that I have in that particular beaker. Okay, so now I know how many moles it is. And I know that that was made by putting the 686.71 milligrams in there. So now I know how many milligrams per mole, right? So I can take that I have 686.71 milligrams over 0.0085 moles. And that'll tell me how many milligrams per mole. Now that's not going to tell me a molecular weight because molecular weights are in grams per mole, right? So I can change this and I can say there are 1,000 milligrams per gram. So I can do a little conversion and that'll give me grams per mole and that'll tell me the molecular weight. So I can take and come over here. I can say 686.71. I can divide that by the number that I calculated, the number of moles. And then I can divide that by 1,000. And that gets me 80.91. Grams per mole. And that's the molecular weight of the HX. Awesome. 80.91. Now, I know that this is made of H and X. And I know that H has a mass of 1.008, right? Because that's what the mass of H is. So I can take that mass, that's equal to this thing right here, and I subtract the 1.008 from it. And that tells me that the mass of the X part, so HX equals the 80.91 minus the 1.008, and that's equal to the 79.90, which is the X part. So I need to look at my periodic table and see what has a mass that's approximately 79.90. And I see that there's something that's roughly 79.90 right here. So if I look to see what that is, that's bromine. And so that X is bromine. And that makes a lot of sense because bromine should have a -1 charge. And so it should be something that can bond with one hydrogen to be an HX kind of deal. So the identity of that acid is HBr. Okay, so the molar mass of the acid is 80.91, and the identity of the acid is HBr. Okay, now I'm never going to ask you to do something that complicated on a test, but that's how you would go about doing it. Okay, you have the capacity to figure out what the molarity of the acid is. You have the capacity to figure out, since it's a 1 liter aliquot of acid, what the number of moles is. You can subtract out the H to find out what the mass of the X is, and therefore determine what the actual X is in that thing. So you know more than you think you do. All right. So questions, comments, problems about that? Hopefully not, but that's where we're going with that. I'm going to take a break at this point and I'm going to pause and we'll come back to this and I will see you guys shortly. All right. I will be back.